Hello all, this is a problem that is a variant of the Atwood machine. We're going to say we have a straight surface, beautiful straight surface here, and we're going to have a box, and we have a drop here with a bit of a pulley. Now, attached to this mass M, we'll call it M1, is another block hanging down, M2. And it's attached via a string like so. So the question is, first, we have one case, no friction. Then we have a second case with friction, with the coefficient of friction both mu sub s and mu sub k. And in this case, we're going to say, okay, well, there are a couple things I want to know. One is A, the acceleration of the system, and then B, we want the if there is a condition where it is static, what is the condition based on the masses? Static or dynamic equilibrium. So for A, the acceleration of the system, we have to take into consideration the fact that we have two free body diagrams here. We have the first free body diagram for M1, where we have gravity pulling down, the force of M1g. We have the normal force pointing up of magnitude M1g. And then we have some tension going to the right. For mass M2, we have M2g, and we have going up a force of tension. Now, the magnitudes of this force of tension here and this force of tension here are going to be the same. Now, if I were to write an equation describing these two situations, I want to look at the sum of my forces. Let's see. So sum of my forces for this diagram, well, we know that we may have an acceleration. Why do we know that? Well, our only force horizontally is our tension. And if the force horizontally is our tension and we have nothing opposing that, well, our net force is to the right. So our force is equal to here, just the tension to the right, and that's equal to m1 times a, its acceleration. Likewise, for the second diagram, I have some force down, some acceleration down, and that is going to equal tension, or m2g minus tension, rather. Now, why would that be? Well, we're going to assume that we have a force pulling down, we have a tension up. If they cancel, then we have no acceleration, but if they don't balance out, then we have some acceleration downward, likely. And that's likely because M1 has no leftward pull, pulling M2 up. So if I add these equations together, I will get M2G equals M1A plus M2A, which in this case, if we want to isolate the mass, we'll find that A times M1 plus M2, the sum of the masses, is equal to M2G divide each side by M1 plus M2, and we get that our acceleration in this case is equal to the force downward on M2G divided by the sum of our masses, which is a situation that makes sense because this force down here has to pull down with one force, the force of M2, on both of the masses and cause the acceleration of both masses. So we're not going to get an acceleration of M2G, we're going to get some fraction of that. Okay, so let's add a layer. Hide this, I'll hide this first layer. And we're going to look at the situation again, this time with friction. Okay, so we have here some value for friction. So let's redraw our free body diagrams. The friction is going to be at this contact point along that surface. There's no friction over here. So let's have a look. Again, we have the normal force and the force of gravity balancing out on M1. And I'll draw on the horizontal forces in a minute. So we have tension pulling up here. We have, tension pulling to the right there. And given that we have a situation where the net force would be to the right, friction is going to try to balance that out toward the left. And the real question is, at what point are we going to have some static equilibrium or eventually dynamic equilibrium? What we're going to look at is and the cases where this isn't, where we have a mass that's too big or too small. In this case, only too big. So our equations are that in the x direction, in the vertical direction here, I have mg, m1g is equal to Fn. That's important. That's a helpful little piece there. We can therefore find the value for our frictional force, a maximum value. So for this diagram, I have the sum of the forces in the y direction. I have the sum of the forces in the x direction, which is that if I truly have equilibrium, then tension has to equal the force of friction, which is, if we know that the force of friction is equal to mu sub s times the normal force, well, here we already have an expression for the normal force. We know that that's the sum of our forces. They're equal to each other, so they balance out, and the net force is 0. On this side, I know that, again, and why are these equal? Well, because I have the situation where I'm in equilibrium. So now if I add up these two terms, I can see that in this case, I can just make a substitution. So anywhere Ct, I can put m2g. So I can see that in this case, the situation where m2 equals mu sub s times m1 dictates the balance of weights where I have equilibrium. What this is saying is that if m2 exceeds mu sub s times m1, then I start to accelerate. And which way am I accelerating? That way. Now, if m2 had a value of 0, what would happen? Well, if m2 had a value of 0, then m1, well, it just sits there because there's no tension force. So this is a descriptor of the situation here. This can be translated to a very similar situation if I have some sort of incline with the pulley, mass on the incline here. And the only difference is that now you have to account for some angle theta. And that angle up from the x-axis, if we flip this around, up from the positive x-axis there, as opposed to the negative x-axis, follows the same rules, except this time we have a component of gravity down the ramp as well. So in this case, we'd have m1, we'd have some tension, we'd have mg, we'd have some normal force, maybe we'd have some friction up the ramp, and there'd be a component of gravity that lines up here of m1 g sine theta, so that's down the ramp, and then in the normal force direction, m1g cosine theta. And so by using those components, you can solve this system in a very similar way. You just have two downward forces down the ramp to oppose the frictional force up. So the terms would look something like this. The frictional force is equal to, the maximum frictional force is equal to mu sub s times Fn, which is m1g cosine theta. And then we have to balance that with tension, which is still m2g in equilibrium. So we have u sub s m1g cosine theta, and then that has to balance with the force of gravity down the ramp plus tension. plus the tension value, which is m2g. And if we want to find the mass ratio, we have to isolate for m2. If we want to find the coefficient of friction, we isolate for mu sub s. And in one case, we just take this expression and move it over to this side, or take this expression, move it over here, and divide by g. So in one case, we'd see that mu sub s is equal to m1g sine theta plus m2g over m1g cosine theta. And we'll see that the g's cancel out. Here. Or we could isolate m2, and again the g's will cancel out, to find that mu sub s m1 cosine theta minus m1 sine theta is equal to m2. So this would be an expression to talk about the maximum value of m2. That's all for now. I highly recommend going through these problems on your own without referencing the video, just to come up with expressions for equilibrium or expressions for acceleration and the like. And change the problem around a little bit, maybe have the angle pointing the other way, or have a situation where maybe you have 3 weights, and see what happens in that case.